Hey, welcome back to the series on the game StackIt. It has been a while since the last video, but I got busy with stuff. I want to continue where I left off. Last time I actually used Vim as my main editor. In the meantime, I switched to PyCharm. It helps quite a bit with readability and formatting and stuff, and I never quite managed to set up my Vim in that way. And you can use IDEA Vim to get the same controls, so I'm gonna go with this now. Coming back to my code, I see many things that I would do different now if I would start again. I also thought if I should restart the whole series because I was not so happy with how it went so far. Lots of stuff got overly complicated and yeah. So what I think would be fun to do today though is to see if we can implement hash tables into our alpha beta search. So if you remember, we finished this last time, then we actually started working on the string representation of the board, and the whole idea behind it for me was that we could use this string representation to generate hashes for our board, for the hash table. But I also think the way I did it is not so nice. Anyway, let's just get started. Yeah, if you remember a little bit alpha beta search, actually in the algorithm I'm using here is called nigger scout. So instead of having a function that maximizes and minimizes, I have one maximize function, and we switch the parameters alpha and beta by negating them, which basically takes care of everything. There's a lot of formatting that's not good here. Auto formatting, nice. Should immediately commit that. Let's see, quite some stuff. Annoying. Okay. Anyway, so the way hash tables work now, and why I think they will give a good speed up for us, is we will check in every state that we have when we search the tree. So we start our alpha beta search. We are at some part in the search tree, and what we do is we generate a hash of the current board position, and we check if we already saw this board position before or not by looking it up in a hash table. And basically every time we go through this loop here, we store in the hash table whether it was a beta cutoff or whether we found a best move or not. I already played around with this before this video to see if I would know how to do it. I'm not entirely sure if we will get the correct version immediately, but we definitely can see some speed up by doing so, and I will double check how to best do it correctly until next time. So I'm just a little bit fuzzy on some of the details. So the way we start is, let's just run our game. And we last time played with this board, I guess, a little bit. By just starting it and exiting, we start the performance tester. Do we? Actually, let me just see, run game. Did I implement perf? I did. Min max. Here I want to use alpha beta. Then we can do it like this. Okay. By starting this board, we can performance test, and then we can just see how far do we go with our current pruning. Immediately here, there's a couple of things that I want to improve upon. Maybe while we let this run, I can check this function, and in here we have AI stats moves made, and what I want to print here is actually let's do dashes with spaces, join. This makes everything a bit more complicated here, but bear with me. So we want to have keys and values, key plus equals plus value for p value in AI stat smooth made dot items. So I found that I want to print a lot more debugging output than just what we see currently, this one field. So I'm just going to take all the items that we store in this stats array. Also, at the same time, we want to basically reset stats every time we go checking for a best move. This is kind of important. And then maybe you can hear my laptop fan spinning up. You can see that from this position up to depth 12, we kind of set on this first move. Our principal variation is here. This is the best possible move order. One thing you also might notice is that every odd number of turns, our score is positive, and every even number of turns, our score is negative. This has to do with the fact that if I make a move and I, for example, push over all of these stacks, then afterwards most of the fields will be mine, right? But I don't account for the opponent having this move next where he throws over this one and then regaining lots of territory. So if we only consider one move, then 1-1 is the best move. It's just throw this over and half of the field belongs to us. So this gives us 15 score. While then in the next turn, the opponent would throw this over. So we can immediately see if we search just one depth further, our best move is -5. This would be after the opponent worked. After the opponent. So this is better than the opponent recapturing. You see we start with 0-2 as the first move, which is this one. So yeah, it doesn't actually matter which one we throw over, but then our opponent would put this stone on 4-4, regaining territory. Anyway, we will wait for one more, which might take quite long, but when I experimented with the hash tables, I saw that if we wait for one more, we can actually see that this will be the victory. Should be. Okay, after doing this, I want to leave this for now and then go back to our alpha beta and actually, instead of only checking how many moves we made, we also want to see, is this called beta cutoff or alpha cutoff? I will call it beta cutoff. So, okay. So now we already track how often do we actually cut off, how many moves do we make. And if you check at improvements to alpha beta search, then hash tables might not be the first and easiest to implement. There is, oh, interesting. So this one does not lead to a win. So this is good to know. Let's store this and then check it for later. So hash tables may not be the best one. One thing that helps a lot with alpha beta pruning is to have a sorting of your moves. Currently, my moves are just randomly sorted, and depending on how the field is, this might search a lot of not good moves before it finds the best move, and after we find the best move, we will do a lot of cutoffs afterwards, because we know other moves are going to be worse, or we know that other moves are going to be too good and the opponent wouldn't let us make them. So what we would want to have is that we start with the best move first. In chess, this might be, there's a couple of heuristics like, oh, if there's any captures that I can make, I will start with the most favorable capture to me. For example, if I can take the opponent queen with a pawn or something, this would be a really good move to start out with. In our case, I haven't found any good, sort of any good way on how to check it. One thing we could do is we could also say, okay, we always start with, if there's a tower that I can top over, I would start with this or something. Or yeah, but this is all just heuristics and not so sure. One way to avoid having to do this by yourself, like thinking about which move is possibly best, there's something called iterative deepening, which instead of immediately starting a search with your maximum depth, you start a search with, for example, depth 1, 2, 3, 4, basically like our performance testing is doing it. And while you might say, okay, but then we have to basically search all of the stuff again. So, if we search to depth 5, we searched all of these 287 moves. But if we search to depth 6, they are included there again. We have to do all of this searching. But what actually happens is we would know which one is the best move from the previous iteration. So instead of searching for move 1, 2, in this case, we can immediately start with move 0, 2. So we start with the principal variation of the previous run. So, by searching shallower depth, we would know, if we start with 0, 2, basically if we start with all of these moves and then just check the last couple of nodes, we might already find one sequence which is so good that the rest of the tree is basically cut off. Yeah, it's interesting that we do not find a winning condition here, which is nice. This also lets me know that my hash table implementation from earlier was probably somehow buggy. I want to store this now. Let's just make a new file for now. We won't commit this. Perfect. And this is just text. And then let's just add this here. As an experiment. So, okay, that was a lot of rambling. I'm still gonna start with the hash tables because I really want to get this implemented. So, we will have a hash table. And we're just going to use a Python dictionary to implement this. The way we're going to do this now is we will store the state of the game. Every time we visit a game, we'll store the state of the game, the best move we found there, the best score we found, and at which depth this was. Stuff like this. So in order to do this, we first need to get a way for our board to have a string representation. Let's go to our board. I know I started implementing this from string method, and technically we should probably implement a toString method which would output exactly this string. But somehow, after thinking about it a little bit, I find this format dumb and hard to read, and I would have preferred to have something like this, where in one matrix, basically, we store with the values of each individual stack, and in another matrix, we store the players array, similar to what we have internally. Because then it gets just so much easier to represent, to create a hash. Also, the parsing would be a lot easier. We still have to store the board size somewhere, but yeah, whatever. So, even though this is super messy, for now I'm going to implement it exactly that way. So we're going to have a function which is toString on our board. What toString is going to do is it's going to make a new instance. No, it's not going to make a new instance. It's going to make a parts array which contains so the current player and myself. So we have the board array, the players array, and the current player. This is basically everything we need to represent the state of our game. If we know all of this information, we can reproduce the current board. A thing that we do not need is the history, because while many boards may have different histories, I'm going to stop this down here. While you may have different histories reaching to the same board, we really don't care about this part. So return join the dot join something like we will just do okay, this is easy for now. It works. We're gonna fix it later so that we have a matching representation of toString and fromString. Maybe I'm even gonna do this off camera because it's not particularly interesting. We encode the current player, then just a string representation of this board array and a string representation of this player's array. This gives us our string, and then we're gonna implement a hash function. Maybe return hash self to string. I'm gonna use the Python hash here, so in between games they're gonna be different, but in between runs, but we do not need to keep this state. So we have our hash table now. So for example, what we can now start storing in our hash table would be self hash table, and at the board.hash position, we want to store the depth at which we found this board. Maybe we even want to find the board toString representation, because hashes could collide, and maybe we want to make sure that our board is really exactly the same. So as soon as we have this string representation, we know the boards need to be exactly the same. Initially, I will not use this though. I guess I should. Anyway. Yeah, I will not use this initially. I didn't in my first one. So we store the depth because once we read this value, we want to know whether the depth we searched from here was more than the current value. We're gonna see it later. We want to know what was the best move, best score, which would be our alpha, I think. Yeah. So we just store the alpha, we store the beta, and we store a type. So one thing we want to know, for example, is whether it was a exact match. Or whether it was a beta cutoff. So, and so alpha beta. So here we have an exact match, which means we searched the tree, we found our best move. And if we ever encounter, for example, this board state again with a depth, with a remaining search depth that is smaller or equal to the depth in the table, we can just use the same move and return it. Also, in case we have a beta cutoff. Wait, here we just break and then we go here. No, I need to think a little bit. Why is there a break? I thought we return if alpha is bigger than beta. It means that we found a move which is better than if our opponent took a different move before. So we want to break and cut off and just return. Na gut. I need to double check if this is correct. But let's work with this, because I actually thought this would be a return statement. Let me just see, is my browser somewhere? No, it's fine. Let's just continue and I will double check this later. One thing is we don't need this one. Okay, so what we can do now is a couple of things. first off, we want to see if we have a hash move, and then we want to say if or entry hash entry. Board hash. And this could fail, so we do save if hash entry. If we have a hash entry, we can unpack it. We can say hash depth, hash move, hash score, hash alpha, hash data. Hash alpha, hash beta, and what was it? Hash type. Hash entry. So if hash depth bigger equals depth, so then we saw this board already, and we can just return hash move, hash alpha, and as a principal variation, I'm just going to return hash move. So our principal variation will be broken now. We'll fix this a little bit later. First, I want to see if I can get this working. And another thing we want to do here is we want to say hash cutoff or exact match. I don't know, hash cutoff. Cool, this would be the first thing. We can just see if this works. Afterwards, we're going to use this hash move. So now, if we were here, we found a best move alpha and a beta. We can say this is an exact match. We're going to use this later because we only want to do this if it was an exact match. And hash type. Let's immediately do it. Otherwise, I forget it. Okay. First. List object. Board. Hashtable get board. Okay. That's why I wanted to test this first. So we did this one, and of course we need to stringify this part. Is it possible to break them apart? Yo, then let's do this. Okay. If we check our old perf, we are at 12, level 12, 13 now, 14 at no time, but we also see that our principal variation changed quite significantly, so something is definitely off. We can see that we do have hash cutoffs, and we can immediately reason about this a little bit. If we think about one move, nothing should happen. Moves made. Let's start on an empty board. This is easier because there we will have a lot of similarities. So let me do board equals board. So we don't have a reset command that would also be time to implement it. So here we have an empty board, and if we run perf here, we will see that now our search depth is a lot less than before. The reason is here now we have actually 25 different moves in the first place, 625s in the next. And you can see there's no alpha or beta cutoffs because nothing happens in the first couple of moves and every move is the same. Like according to our scoring function, if I put something here, the opponent puts something here, I put something there, the opponent puts something there, there's no difference in score to that. So we have to actually search the whole tree, which is kind of not good. And we might want to implement a scoring function, which, like for example, it's better to be in the middle or something. One reason why I don't necessarily like doing this is because it already imposes some me knowing that maybe it's better to be in the middle. I don't know this. Maybe it's better to be in the outside. Who knows? So you can see we don't go very deep. But I would have expected that. Ooh, it doesn't reset the state. Interesting. But here you can see this is one actually at depth 4, a board, and this one is the same as any other board where we just placed randomly in different locations. So there will never be a beta cutoff. I think these beta cutoffs probably come from someone toppling over a tower and then the opponent toppling over his tower, and then, you know, at the end it's worse for you. But what I wanted to do is now, if we check, we have had hash cutoffs here as well, but we should have probably had cutoffs here as well. And I know why we didn't. Okay. Now, what happens is we run our perf. Perf every time instantiates our class from the beginning and gives the max depth, and then says, hey, I want to know the best move until here. So this hash table is empty, this hash table is empty, this hash table is empty. And in the first 2 moves, there is no repetition possible. So I don't know, if I place something here and you place there, then what's possible is symmetries that, I don't know, if we rotate our board, we would have a match, but there's no other way to get to this state. Only with 3 moves, let me think. I place here, you place there, I place there. Should be the same as I place here, you place there, and I place there. But at depth 3, this doesn't matter because we do not try to search more. This is already, we're then already in the 0, category, and we just return a score. So 4 is the first time where we see this happening, where, oh, if you place here, or if I place here, you place there, I place there, it's the same as I place down here, you place there, I place there. And this is where these permutations come from. Now we would have to run this without hashing. Just to get an idea on if this is already happening. This is gonna take some time. So here it took us with these hash cutoffs, and you see this is actually a lot more than beta cutoffs. It took us 10 seconds. I expect this here to take a lot longer. Let me think why this would not produce the correct result. So 23, it's almost twice the size. We should have the same amount of beta cutoffs. Yeah. And the same principal variation. This is another thing. The principal variation here may or may not be slightly random. You can see the score here is 0 because nothing happened, and the principal variation is basically just everyone playing in order. So I play here, you play there, I play here, you play there. And the only reason we do this is because this is the order in which we start searching for the moves. So the first move we take will be the best move because it's as good as every other move, and this strong bigger than will never be satisfied. One thing we can do is actually we can reformat this code, and we could shuffle our moves until we know how to. Wow. This is move. Let's shuffle. Oh, shuffle is in the random module. It doesn't matter. We could shuffle this so that they don't always make the same exact moves. You can see 5. Did we manage to do 5 here? No. But this takes forever. I'm gonna kill this. I'm gonna exit. Now back to the question on why we get different results than before. I assume it should not be that we have hash collisions yet. I mean, we might store a couple of 100,000 keys in our hash table, but I remember this working a lot better. Anyway, this is already a 30-minute episode. I was rambling a lot about it in the beginning. So we just gonna make a shortcut here. I'm gonna look it up if I find anything that's wrong, and also check on this alpha beta whether this is actually a break or a return. And yeah, see you in the next episode.